Well, if we say we're going to be taking an algorithmic approach to number theory, let's talk about flowchart algorithms. What are flowcharts to be used as algorithms? Well, an algorithm is a list of clearly defined, totally unambiguous steps. Usually it's going to begin with some sort of input and generally ending with some sort of output, although technically that's optional. So we're going to be working with algorithms as flowcharts. There's other ways people talk about algorithms, either specifically coding them in a certain programming language or using pseudocode. We're going to be using flowcharts. So a flowchart has a collection of nodes that are connected with arrows. And from one node, you move to another node, depending on what arrow points where. And we're going to learn all the various ways this works. There will never be any ambiguity as to where to go next. It's not possible based on how these are put together. There are rules about it. So the purpose is to take some sort of common problem and reduce it to a specific list of instructions that, if you follow them, will always give you the correct answer. There's a lot of types of problems we introduce in this course. Find the greatest common divisor of two numbers. Solve a system of linear modular equivalences, things like this. And it's important, and you're going to be tested on being able to solve them, and there's always a totally unambiguous list of specific steps that, if you follow them correctly, will give you the correct answer. And if you can simply learn to approach these problems as not requiring you to invent new techniques and be clever, but rather execute the same collection of steps every time, you'll come to learn that these are not difficult problems. It's just a matter of following the instructions. So we're trying to take out of the computational side of this course any requirement to be, quote, good at math, end quote. You just need to be able to follow a list of instructions. So what are the various types of nodes that we're allowed to put into our algorithms? We're really only ever allowed to use 4 different types of nodes. The first is a start or a stop. It's an oval, it's red. Okay, it has exactly one start node. That's where you begin the algorithm. You are not allowed to have any arrow pointing to your start, but it has exactly one arrow pointing away from it. An algorithm has to have at least one, but maybe more than one nodes labeled stop, which tells you to just end whatever you were doing. This is the only node that has no arrows leaving it because the algorithm is now done. There are input-output nodes. We use parallelograms that aren't rectangles, and we're going to color them green. So input nodes prompt the user to input a value of a particular type, and we're going to assume that the user always puts in the correct type of value. For example, if it's labeled that it's supposed to be a whole number, you get to assume that the user does that. Okay? There's only one arrow leaving them. Output nodes will output some sort of value, and they also have one arrow leaving them. A computation node is a white-filled rectangle. They perform some sort of computation on existing data, changing the value of an existing variable or declaring the value of a new one. They have one arrow leaving them. Okay? They can also be used to call upon algorithms you've already defined. We're going to see how very, very useful this is. A decision node of this blue diamond. Okay? These have a statement in them which is either true or false. This is the only node with more than one arrow leaving it, and it must have exactly 2. One is labeled with a true, the other is labeled with a false. Depending on whether the statement inside is true or false, you follow one arrow or the other. This is it. These are the 4 node types. Your start, stop are your red ovals. Input, output, your green parallelograms. Computation, your rectangles. And decisions, your blue diamonds. So let's see some of these in action. An algorithm, remember, has to have one start node, and that's where you begin. You're not allowed to have any arrows pointing towards it. It has exactly one arrow pointing away from it. Then it has to have at least one, but it can have more than one stop node, which signals that the algorithm ends. And this is the only type of node, the stop, that has nothing leaving it. So for example, here's an arrow leaving a start node. Okay, it's got to have one. It can't have more than one. Your algorithm has to have a single unambiguous place to start. Okay, and this should be the only node with nothing pointing to it. If there's another node in your graph with no arrow pointing to it, then you're never going to get there, and it doesn't need to be in there to begin with. Okay, it's not illegal to have other nodes with nothing pointing to it, it's just bad practice. Okay, it has one arrow leaving, which tells you where to go next. Here's a stop node. It happens to have 3 arrows pointing towards it. Okay, every algorithm has to have one, but it can have more than one. It's never actually necessary to have more than one, but it might be convenient for how you put the algorithm down on the page. Okay, this is the only type of node that has no arrow leaving it because you don't need to know where to go next because you're done. How do input-output nodes look? So remember that they prompt the user to input a particular value of a particular type, and you get to assume that the user has done this correctly. In general programming, by the way, you have to be very careful that your user doesn't input values of the wrong type. If you ask them to input text and they input a number, you want to make sure that isn't bad. Okay, but we're going to take the enormous luxury of assuming that our users are always inputting values of the correct type. They have one arrow leaving them. Output nodes, okay, output some sort of value, and they have one arrow leaving them. So here is a input node, and it specifies that you are to input a and b, which are 2 natural numbers, and a is bigger than or equal to b. Okay, it will now have one arrow leaving it, which I haven't drawn. You get to specify what sort of data is being input. In this example, a and b have to be natural numbers, and you get to assume from this point forward that they are. You also get to put restrictions on your input. It's not necessary to, but in this example, we have specified that a must be bigger than or equal to b, and from this point forward, you get to assume that you really did input the correct type of data. So if these variables already have values, if a and b already existed, this input will overwrite them. So if a and b were already given values earlier in the algorithm, at this point, they would be replaced with whatever was input. Here's an output node. Okay, it's going to have one arrow leaving it. Okay, you're only allowed to output something that exists. Okay, you can output something specific like output true or output 7. If you output a variable, it had better be a variable that already has a value. Okay, you can do something like output a computation. So if a has the value 2, you can output a plus 3. And this is kind of bad practice. Okay, I'm going to try to avoid combining computation with output. I'm going to try to separate this into 2 steps. For example, first compute a plus 3 and then output that. But sometimes that just takes up too much space. So if it is necessary to do this sort of combining a computation with an output in order to make an algorithm fit on a page, I'll do it, but I will try to avoid it. Okay, so otherwise, try to keep your computations and your input-output separate if you can. What's a computation node? One of these white or gray rectangles. So this takes some data that exists already and performs changes on it, or it declares a new variable. Okay, and again, we're going to have a single arrow leaving them. They can call upon algorithms that already exist as well. So here, for example, is a computation node. It will now have one arrow leaving it. The arrow inside the box, this sort of backwards pointing conditional arrow, is the gets symbol. And what this tells you is a gets the value of a plus 1. The computation on the right is done first and then substituted for this name. Okay, so first compute the thing on the right and then call it that. So the thing here has to be an existing variable, and everything here has to already exist as well. So in this node, suppose a already exists. Suppose a already has the value 4. This says compute 4 plus 1. Okay, that's 5. Take that value and stick it as the variable a. So before this node, a was 4. I then computed 5 and called it a. After this node, a is 5. Do this computation and then call it that. This box, by the way, is a very common computation that we'll do. Whatever the value of a was, increase it by 1 and call that a instead, and then keep going. This is what's called an incrementer. It just says whatever the value was, increase it by 1, and store that as your new variable. Okay, or a counter, sorry, they're also called counters. Take an existing variable and increase its value by 1. Here is a different symbol, this colon before the equal sign. This will now have one arrow leaving it, and this symbol is used to declare a value of a new variable. So the variable a never existed up until this point, and this special symbol says, invent the new variable a and give it the starting value of 13. It's not really much difference from a gets the value 13. The only distinction between this symbol and this one is that this is very specifically used to declare a new variable that has never existed. This would require a to already exist as a variable and give it the value 13. There are certain programming languages that require you to declare your variables as a separate step versus giving them values, and this is to kind of honor that, but it's not really a huge distinction for our purposes. So we're really not going to be too concerned. If you write flowchart algorithms and you have something like this, where a never existed and now you're giving it the value 13, everyone's going to know what you meant. Make a new variable and give it the value 13. So if you don't want to keep track of the distinction between this symbol and this one, that's not such a huge deal. Okay, now here's an example where we are computing something and assigning it the value of a, but what we're doing is we are calling on an algorithm that already exists. So here, sum would be an algorithm that inputs two numbers and outputs one. And let's suppose we've already written a code that does that. So this algorithm would require the user to input two numbers, a and y, and then it would output a single number. And what we're doing here is saying, rather than recreate that entire algorithm, assume I'm allowed to do it and store that as the value of a. So assuming a and y both have values and we have an algorithm that can compute the sum of two numbers, this does that and stores it as a. Now to begin with, what computations are we allowed to do? All we're allowed to do to start with is add 1. I can't even add 3 plus 5. For the purposes of our discussion, I don't know how to do that yet as an algorithm. The only thing our computer can do as a built-in operation is add 1. That's the only computation. So I can store a value. This doesn't require any computation at all. I'm allowed to add 1 and then store it. This, I have no idea how to do it yet. So let's discuss how to use the blue diamond decision nodes. Inside the node, remember, goes a true-false statement. These are the only types of nodes with more than one arrow leaving them, and they must have exactly 2 arrows leaving them. One is labeled true, one is labeled false. For example, here. Again, to stress, this is the only type of node with more than one arrow leaving it. When I see an algorithm with a gray computation node with 2 arrows leaving it, I get confused because I don't know which way to go. If I see a blue diamond with 1 arrow leaving it, I get confused because what if what's inside is true or false? It's got to have exactly 2 leaving. If I see a blue diamond with 3 arrows leaving it, I don't know what to do. Okay. One mistake people sometimes make is they'll label these arrows with statements. That's not how this works. The statement goes in the box. Then you have 2 arrows, one if true and the other if false. So the thing inside has to be a statement. It's either true or false. It can't be both. Remember, that's what a statement is. Then you have the 2 arrows. Follow one arrow for true, follow the other arrow for false, and those are the labels, true, false. So in this example, if a and b are already numbers that have values, there's an unambiguous choice as to which arrow to follow. If a is bigger than or equal to b, I'm going to follow this arrow and do whatever it says. If a is not bigger than or equal to b, I'm going to follow this arrow and do whatever it says to do next. Depending on a and b, I may go one way or the other. But when a and b have values, there is only one way to go. So what decision nodes are we allowed to use? Okay, I already mentioned the only computation we're allowed to do for now is to add 1. The only decision we're allowed to make for now is the one that's above. If you have 2 natural numbers, determine which one, if one is bigger than or equal to the other, that's the only decision. So if you ask something like, is x prime? I have no idea how to evaluate that yet. Okay, the only decision I can evaluate is, given 2 natural numbers, ask if one is bigger than or equal to the other. Well, as is tradition, our first algorithm is going to be the hello world algorithm. All it does is start, output the text hello world, and then stop. Here it is. It's not very complicated. No matter what, when you run this algorithm, what do you do? Well, the first thing you do is find the start node. There's only one, because there has to be one, but only one. So find it and start there. It has one arrow leaving it. Follow it to this node. This node says output the string of text hello world. Then follow the only arrow that exits that, because only one arrow can exit any node other than a decision node. And then I am at the stop node, so I'm done. So that's it. Okay, start, output, stop. What we want to do now is determine if we can actually check if two integers are equal. But remember, our only decision that we have built in to begin with is if A is bigger than or equal to B. So how can I use this one built-in decision to actually check if two integers are equal? Well, here's an algorithm that does it. First, let's check if this algorithm is legitimate to begin with. Does it have a single start node? Yes. Does it have at least one stop node? Yes. Other than that, let's just make sure everything has exactly one arrow leaving it, except for the stop node, which has none, and decision nodes that get exactly two arrows leaving, one labeled true, one labeled false. Single arrow leaving, single arrow leaving. This is a decision node. It has two arrows leaving, labeled true and false, respectively. Decision node has two arrows leaving, labeled true and false. This node has one arrow leaving. This node has one arrow leaving. This node has none, which would be bad, except it's the stop node, and that's the single node that is allowed to have no arrows leaving, and in fact must have no arrows leaving. Okay. Now, why does this algorithm actually check if two integers are equal? Well, let's try to run through it a little abstractly. I start here, then I input two natural numbers. So I have two natural numbers, A and B. I'm trying to check if they are equal. Well, if A bigger than or equal to B is false, then A must be smaller. So if A is smaller than B, I'm going to follow the false arrow and say false and stop. What if A is bigger than or equal to B? Then I check, is B bigger than or equal to A? This is another decision that's built in. Given two values, I can check whether one is bigger than or equal to other. Well, if this fails, then B was smaller than A, in which case they're not equal and I still want to output false. Actually, the only way I'm ever going to output true is if I go true here and true there. So if both of these things are both true, then I'm going to output true. A is bigger than or equal to B, and B is bigger than or equal to A. How can I possibly have both of those things true if they were the same number? In other words, if A equals B. So if A equals B, this is true, and this is true, so I output true, because A was equal to B, and then I stop. If A and B are not equal, one of them is bigger than the other. If B is actually larger than A, then this statement is false, and I'll say overall they weren't the same. But if A is larger than B, then this one would be false, and I'll say they were not equal to begin with. So just using the single built-in decision, R is one number bigger than or equal to the other, overall, this will tell me they are not equal, they are equal. So now, what we're going to do is we're going to allow a decision node to just directly check if these are equal. Because I have an existing algorithm that determines are these two things equal or not, and outputs either false or true. From this point forward, I'm going to allow myself to build a blue decision node and just ask, are these two things the same or not? Well, if they are, I'm going to go one way, and if they aren't, I'm going to go the other, and I'm using the fact that we have already determined this algorithm here. Okay, notice you can actually get the same result with this compound statement, A bigger than or equal to B and B bigger than or equal to A. I could have just made a single node that asked that. That's still a statement. It's either true or false. That would be okay, but it doesn't quite show the sort of flowchart-y structure that we're going to ultimately be using a lot. So here's that algorithm again. Let's check it. If I input A equals 10 and B equals 7, what's going to happen? Well, I have to start here. Then I move to the input node and I input a equals 10, b equals 7. I said that's what I want to do. Then I move to this decision node. So I check, is a bigger than or equal to b? But a and b have values, specifically 10 and 7. 10 bigger than or equal to 7 is true, so I'm going to follow the true arrow. So now I'm here, and now I ask, is b bigger than or equal to a? Is 7 bigger than or equal to 10? Well, that's false, so I follow the false arrow. So I output false, and then I stop. So indeed, if a is 10 and b is 7, and I check, are they equal to each other? I got the correct output, false. They're not equal to each other. What about checking for a strict inequality? Well, since we're allowing compound statements, we can use the two decisions we've already done. We're allowed to check if a is bigger than or equal to b, and we've just devised a way to check if a equals b. So since we're allowing for modifiers, we could also check, is it not the case that a is equal to b? So we could make the compound statement, a is bigger than or equal to b, and a is not equal to b. That would be equivalent to asking a is bigger than b. It's bigger than or equal to, but it's not equal to. So rather than build the following, okay, this is a single decision node with that compound statement, we're just going to allow this. Again, once you devise a way to test a new statement, from that point forward, it's a statement that you're simply allowed to test. As we build more and more complicated things, we're going to use them as single steps in other algorithms. This is how we build up the ability to do progressively more difficult computations, having only started with the ability to add 1 and the ability to ask, is a bigger than or equal to b? Well, now I can check if they're equal, and I can also check if I have a strict inequality. So what about the successor function? Let's start working with computational nodes. I already remarked the only computation we're going to do is add 1. So here's an algorithm which takes as an input a natural number and outputs the one that's 1 larger. Not very complicated. There's not a lot to do here. You start, you input a natural number, I compute that plus 1 and store that as the value of a. This is the only computation we're allowed to do at the moment. Then I output a. Notice that even though a was input and a was output, the output is not going to be the same value. So let's check what happens when we input 5. We start, we input 5, I compute the value of 5 plus 1, and I store that as a. So now a has the value of 6. Then I output a, but a has been changed. It now has the value of 6, and then I stop. Well, how are we going to make new functions that do more than just that? So our options start to really develop when we allow for naming new functions that are then called upon in other ones. So for example, here's an algorithm that determines which of the two numbers is bigger. Notice it starts, it takes two natural numbers, it asks if is a bigger than or equal to b. If so, output that one. If not, output b. Either way, what are we outputting? The number that was bigger, and then stop. We declare this to be called the maximum function. For two numbers a and b, the maximum simply outputs whichever of the two numbers was bigger. So since we developed it as an algorithm here, anytime I have two natural numbers, I don't have to replicate this entire diagram if I want to produce the one that's bigger. I simply say, I've already done this and I called it maximum. So use that as a single computation. So how would I find the largest of three numbers? We could design a whole new algorithm, similar to the way we devised the maximum of a and b, or we can use the fact that I already know how to find the maximum of 2. So here is a way to start, input 3 numbers. Out of the two numbers a and b, find the one that's bigger and call that a. Then, out of a and c, find the one that's bigger and call that a, and then output a. So what have we actually done? If a was the biggest of all three, what's the biggest of a and b? It's a. Okay, then what's the biggest of a and c? It's a. I'm going to output a. What if C is the biggest of all the three numbers? It doesn't really matter what happens here. At this stage, the maximum of A and C is going to be C, and then that gets stored at A, and that's what's output. What if B is the largest? Then here, I'm going to choose B and call it A. At this stage, this does refer to A, but in the previous box, it got that large value, in which case I'm going to choose it again, and I'm going to output that large value. So no matter what, out of the trio of numbers, by checking, pick the biggest of the first two, then pick the biggest of that and the third. I'm going to find the largest value and output it. So input three natural numbers, replace the first number with what was bigger out of the first two, then replace the first number with that earlier one and the last number, whichever is larger out of those two options. Okay, so in that second computation block, the one up here, this A might not be the same as the one back here. This A is going to be the same as what was computed in the previous block, the maximum of the original two first numbers. So let's check it. Let's input A equals 3, B equals 5, and C equals 2. Well, we start at the start. I move here and I input what I said I wanted to. So now A is 3, B is 5, C is 2. What I now do is I compute the maximum of A and B. A was 3 and B was 5. So what's the maximum of that? 5. And now that's the value of A. I moved here and now I ask what's the maximum of A and C? But remember, A is now the value 5 and C was 2. So what's the biggest out of 5 and 2? It's 5 and I store that to A. So now I output A, which is 5, and then I stop. So by combining these two maximum checks, what we're really doing is checking for the maximum of all three. And now we could allow that as a single step, find the maximum of 3. In theory, I still haven't developed a way to find the maximum of 4 numbers, let alone the maximum of a list of unspecified length, but it's kind of clear how you would do it. At least for 4. If I don't know how long the list is, it's not immediately obvious how many times I need to chain together this kind of computation here. If the length of the number of things we're going to have to compute depends on the input, in other words, I don't know how long the list of numbers is, but I want to find its largest element, what we're going to have to do is develop what's called an iterated algorithm, an algorithm that repeats a certain operation an unknown number of times.